Alright, this is part 3 of the video solutions to the final review. Here we're looking at another exponential equation. It is 1/3 to the x power equals 81. And so there's two types of exponential equations. The first type is, can we get the bases to look the same? The second type, we can't do that, and so we'd have to use some sort of log. Now in this one, the common base here is going to be 3, but we're going to have to work it a little bit. So 3 to the 4th is 81, and then 3 to the minus 1 is going to be a 1/3. And what we're going to do here is we're going to go ahead and rewrite, replacing the 81 with 3 to the 4th and replacing the 1/3 with 3 to the minus 1. So we'll go ahead and do that. And we're going to use the fact that b to the m to the n is equal to b to the n, m times n, so that's if you raise a power to a power, you're going to multiply your exponents. So we get 3 to the minus x is equal to 3 to the 4th, and then we're going to use equal bases equal exponents. Exponentials 1 to 1, and so that'll tell us that minus x is equal to 4, and so we'll divide both sides by -1. And so that's going to tell us that x is equal to -4 in this problem here. Okay, so number 22, we have e to the 4x minus 1 is equal to e squared to the x. And so the first thing we're going to do is we're going to use the fact that b to the m raised to the n, multiply those exponents, b to the m times n. So that's e to the 4x minus 1 is equal to e to the 2x. And here we're going to use the fact that the exponential is 1 to 1, equal bases equal exponents again. So x is equal to y. In this case, that's 4x minus 1 is equal to 2x. So this is a nice linear equation. We'll subtract 4x from both sides. And then we will divide by -2. And that's going to get 1/2 is equal to x there. Okay? Alright, and the next one we're going to look at, they say 5,000 is going to be deposited into, let's speed it up a little bit, into account paying, how much interest is that? 3.1% interest compounded continuously, and they want us to find the total in 5 years. And then they're also going to ask us, well, they're just going to tell us find the total in 5 years, and then they're going to ask us how long does it take to double. Continuously compounded, that's the PERT equation, A equals PERT. We're going to go ahead and extract the information there. So you have two number value, or two dollar values, that's the amount and the principal. A is sometimes your future value, or your sometimes just called the amount. P is your principal or your present value, so, and oftentimes that's the amount we're going to deposit. So P is 5,000. That's what we're going to deposit. Your interest rate is a decimal, so 3.1%. If we want to convert that to a decimal, we need to move that decimal place over twice. 3.1% means 3.1 per 100, so that gives us the justification for moving that decimal place over a couple of times. Alright, let's move this stuff off the screen. Okay, and t is 5, and that's what they're asking us to do. So we just plug it into the formula. 5,000 e to the 0.031 times 5. We'll write it in how most likely your calculator will take it. The parentheses is absolutely essential there in the exponent, so oops, we don't want to erase, I just wanted to highlight there. So those are absolutely essential. If you don't do that, then it's going to raise it to the 0.31 and then multiply by 5, which is not what we want it to do. So after those 5 years, we're going to have $5,838.29. If we want to find the double, double that initial value will be 10,000. We started with 5,000. We're going to assume the same interest rate, but this time we're looking for the doubling time, so we will not know what the time is. So A is 1,000 equals P, which is 5,000, E raised to the 0.031 times T. So the first thing we're going to go ahead and do here is we're going to isolate the exponential, so that is going to require us to divide by 5,000. And what's going to end up happening is on the left hand side is going to be a 2, so the doubling time will be the same for this interest rate every time. So now we've isolated the exponential, and now we're going to take the natural log of both sides to undo the exponent. So we get the ln of 2 equals the ln of e to the 0.031t, and we'll mention that the ln and e are inverses of each other, so they're going to cancel out, and you're going to be left just with the exponent. And so we're going to have the ln of 2 is equal to 0.031t, and we'll divide both sides by 0.031, and that will give us approximately 22.3 years. Okay, and so the strategy we used in class is, if we're doing some sort of compound interest, look for if it says continuously. If it says continuously, then that's the PERT equation, and then we write down all the information somewhere, kind of organize what we have going on, what are we missing, and then we proceed from there. Alright, so I think we probably have another one of these. Okay, so what amount deposited today at 3.1% interest compounded annually will grow to 6,000 in 5 years? And so they don't have the word continuously, so this is going to be the standard compound interest formula, which is amount equals principal times the quantity 1 plus r divided by n raised to the nt. We'll go ahead and write down all our stuff. A is your future value, or your final amount. P is your present value, or what you're going to deposit. Maybe if it's a loan, that's the amount that's loaned. R is your interest rate as a decimal. N is going to be the number of compounds per year. So oftentimes that'll be annually, which is 1. Biannually or semi-annually would be 2. Quarterly would be 4. Monthly would be 12. Daily would be 365. Those are the usual ones. This one says compounded annually, I believe. Let me double check. Yep, compounded annually, so that's going to be 1. And then the time is 5 years. So let's go ahead and put in what we want. We want it to grow to $6,000, so that's our future value. We don't know how much to deposit, so we don't know what our present value is. That's what we're tasked to find. Interest rate is 0.031. N is 1 and T is 5. So we'll go ahead and put that all into the formula here, and we'll go ahead and simplify down what's inside the parentheses because it works out pretty nicely. Sometimes it doesn't work so nicely, so sometimes I would suggest to leave it as is if you get some sort of messy decimal. So now the 1.031 raised to the 5th power, that's connected by multiplication. We don't need any ln's because we're not solving for an exponent. We're solving for the p there that's just being attached to this by multiplication. So we're going to divide by that. So we'll divide both sides by 1.031 to the 5th power. Okay, and so the present value, or how much we should deposit today, should be $5,150.60, and then in the 5 years that'll grow to $6,000. Okay, so what are we looking at now? Okay, so we got e to the 2x is equal to 500, and I think they want us to solve an exponential equation. So the first thing we're going to look at is our exponential isolated? And absolutely it is, so we'll go ahead and take the natural log of both sides. And because e and the ln are inverses, we can use our inverse property, which says the ln of e to the x is equal to x, or whatever the exponent is. In this case 2x, and that's going to be equal to the ln of 500, and then we'll go ahead and divide both sides by 2, and so we get x is equal to the ln of 500 over 2, and we can give you a decimal value that's 3.1073. Okay, Alright, so let's solve another one. 5 to the x is equal to, let me double check here, I think that's a 13. Okay, 13. So first thing to do is we're going to isolate the exponential, or look to isolate the exponential, but it's already isolated, so that's good to go. And so afterwards we're going to take the natural log of both sides, and then we'll use our power rule, which is going to bring down that exponent of x. So we'll mention that here in blue. Ln of b to the r, the power rule is going to take your exponent and bring it down in front. You can do this with any log, any valid log base, but I like ln because it's less writing and it works nicely with e. Okay, and that's our power rule. So that's going to bring that x down. X ln of 5 is equal to the ln of 13. And the ln of 5 is a number, so we can go ahead and divide both sides by that. So we are going to have x is equal to the ln of 13 over the ln of 5. And we could put that in our calculator. I forget if I ended up putting it in the calculator. Nope, looks like it did. So then I can get a decimal value for that. So 1.5937 is our approximation there. Okay. All right, let's look at another one here. Now we're going to transition to looking at a log equation. So we have log base 5 of 8 minus 3x is equal to 3. And so our strategy for log equations is to isolate and condense logs. Well, there's only one log, and it's already condensed and isolated. So we're going to rewrite it. So log base b of x equals y is equivalent to b to the y power equals x. And so in our problem, we're going to identify our base as 5. And our exponent is 3, so 5 to the third power is equal to 8 minus 3x. That's 125 is equal to 8 minus 3x. We'll subtract 8 from both sides. We'll have 117 is equal to negative 3x, and then we'll divide both sides by negative 3, and we'll get negative 39 is equal to x. Okay, and usually we check to make sure that our answer is not negative when we plug it into the log. So when we plug it in, we'll have 8 minus 3 times negative 39, and so it's going to be positive, so the log's going to be okay with it. Remember, the log's a happy creature, doesn't like being fed anything that's not positive. Okay, so let's take a look at a log equation here. So we got log base 5 of x plus 2 plus log base 5 of x minus 2, and that's going to be equal to 1. So again, our strategy is to condense the logs and possibly isolate. So the rule that we're going to use here is the product rule, because we're adding two logs of the same base, and so we will condense them down into one log, and you'll multiply the arguments of the logarithm. Okay, there's your product rule. So this becomes log base 5 of x plus 2 in parentheses times x minus 2, and then equals to 1. And then we'll go ahead and FOIL the x plus 2, x minus 2, and then we're going to rewrite. So it is log on one side, so that's going to be b to the y power equals to x, or in this case, it's going to be 5 to the first power, and that's going to be equal to x squared minus 4 after you FOIL x plus 2 and x minus 2. So you have to FOIL that first. This is quadratic, so we want to set it equal to 0 and cross our fingers that it factors. And it will factor. It'll factor into x minus 3 and x plus 3. It's a nice difference of squares. Okay, and so that's going to give us the value of 3 and minus 3. However, minus 3 is not going to be good, because if I plug it back into, for say, x plus 2, that's going to give us a negative. Log's not going to be happy with that. But however, 3 will be okay. It'll like the 3. Alright, so we're on to almost the last one here. So ln of 3x minus 2 minus the ln of 4 equals the ln of x minus 2. So we're going to go ahead and condense the logs. This time we're subtracting logs of the same base, and so we're going to use the quotient rule. So we're going to squish those logs together, and then my shortcut is a positive on the top, negative on the bottom. and then we call that the quotient rule. So that's the first thing we're going to do, is look to isolate and condense the logs when we have an equation involving logs. That gives us 3x minus 2 over 4, and that's going to be equal to the ln of x minus 2. And we did have a problem like this on, well, kind of like the last 2 or 3 problems we've had on this last test here. So it can be a good review as you prepare for the final. Or maybe you're watching this in the future and you're getting ready for exam 4. Now we're going to use a different property here. We have log on both sides, so we're going to use the one-to-one property, so the arguments are going to be equal to each other. So it's kind of like equal bases, equal exponents. Some people like to say the logs cancel. And so that's going to give us 3x minus 2 over 4 equals x minus 2. That's what pops out. We'll go ahead and clear the fraction here. We'll multiply both sides by 4. 4x minus 8. And then we'll go ahead and set one side. Well, we're going to isolate the variable. Sorry, I'm battling the cat here, he's trying to step on the screen here. So I elected to move the x terms to the right, so I subtracted 3x, and then the minus 8 on the right hand side, it doesn't have an x, so we're going to add that to the other side, and so we get x is 6, and then we can run that through our logarithms, and we don't get any negatives, so that's okay. Okay, so we got one more. I'll try to keep the cat at bay here. So what do we got going on here? Alright, so let's speed it up a little bit. Find all the roots of x cubed plus x squared minus 17x plus 15. So this is a cubic, and we're not going to be able to do this unless it's with like factoring, unless it's like something we could do factor by grouping, and we can't do that here. So we're going to use the rational roots theorem. So it's going to be the factors of 15 over the factors of 1, which is the leading coefficient here. So it's the factors of the constant 15 over the factors of the leading coefficient, that is 1. So I loosely use it as p's over q's. So we're going to look at the factors of 15 over the factors of 1. So factors of 15 would be 1, 3, 5, and 15. And then technically we would divide them by the factors of 1, but there's only 1 and negative 1. So that's what I need to look at. Now, I can always check very quickly if 1 works by adding up the coefficients. So 1, 2, adding that would be negative 15, adding that positive 15, that's 0, so I know right there that 1 is going to work. So we're going to go ahead and do our synthetic division, write our coefficients, 1, 1, minus 17, and 15. And then we're going to try 1 out first. If 1 didn't work, then we'd go back to our list and try something else. Okay, so first thing to do is bring down that first 1, and then you're going to multiply this by 1, and that's going to give us that. And then we'll add 1 plus 1 is 2. And then we'll multiply 1 times 2, which will be 2. And then we'll add that to the negative 17, which will give us negative 15. Multiply one more time, and we get a remainder of 0. And if you want, you can draw the creepy happy face for your smiley face, for your 0, not your smiley face. Anyways, so we got 1 works, so we'll say that's a root or a 0. The factor is x minus 1. And so what we got left going on there is your remainder, which is 0, your constant, which is negative 15, your x is 2, then you have an x squared. If you had more stuff there, then that'd be, you know, x cubed and x to the 4th, and etc. there. Looks like the contact's not working so well. Okay. Anyways, so that's x squared. Uh-oh, I think I undid too much there. Okay, plus 2x minus 15. And what we're going to do is we're going to try to factor this, and it factors nicely. X plus 5 and x minus 3 equals to 0, so that gives us roots of negative 5 and positive 3. So we'll drop those into our chart here, and so we have all our roots. Our roots are 1, negative 5, and 3. I don't think they ask for the factored form, but oftentimes they'll ask you for factored form, so if you got all the roots, then it's pretty easy to write your factor form also. So we'll add that in as an extra piece here. Okay, and so that's it for part 3.